Okay, so today we're going to start something new, right? It's going to be a little bit different. Luckily, there's not a lot of like math. Well, there is math, but it's not like doing the orbitals and doing the doing the electron configurations and figuring all that stuff out. And so it's going to feel a little bit different today, all right? So today we're going to talk about intermolecular forces. Okay. So last time we were talking. We were talking about those molecular orbitals, atomic orbitals, because we were talking about actual chemical bonding, right? The ionic bonds and the covalent bonds that hold atoms together because they want to stabilize, because they want to have a full octet. Remember that? So that's why we're talking about that. So those are not the only kinds of molecular interactions there are, right? There's also the intermolecular forces. I thought I would do my lecture today with a happy face laser. Maybe that would be. Oh, it's hard to see. It's kind of hard to see. Oh well. We'll just go with the dot. Okay. Well, I wanted to do a happy face. That didn't work out. So there's more than just the covalent bonds and the ionic bonds, right, that we do in chemistry. There's also the intermolecular forces. Okay. So intermolecular forces are attractions between molecules, right? But they're not as strong as bonds. Okay. They're just attractions between molecules. And these intermolecular forces, they affect things like the boiling point of certain elements, the melting points, the viscosity, the surface tension, and capillary action, which we'll go through each one of those in a second, right? So the first thing we have to talk about then while we do this is the states of matter. I know it's a review from basic high school chemistry. What are the states of matter, right? Liquid, solid, and gas. At least that's the ones that we're going to talk about in here, right? Liquid, solid, and gas. So stronger forces bring molecules close together. Kinetic energy keeps them moving and apart, right? So you heard me say this before. Even though this table here is solid, there's definitely kinetic energy in this table, and the molecules in the table are vibrating, right? But the extent that these molecules are vibrating will tell you whether or not these things are solid, right? Or if they're liquid, like the water bottle, not the water bottle itself, but the water inside the bottle, or the vibration, the gases in the air, right? So we talked about before, we had chlorine gas right here, right? Obviously, it's a gas, right? And it's floating around in the flask right there, the Erlenmeyer flask, and you can see that the chlorine molecules are actually super far apart, right? Whereas in a liquid, they're a little closer together for the bromine, right? And then in the iodine, they're actually solid. They're super close together. So the reason why I wanted to show you this particular picture is because when you look at the periodic table, all of those are what? They're halogens, right? In group 7. Okay? And as you get further and further down the table, right, what happens to the atoms? They get bigger, right? The radius gets larger. The atoms get bigger, right? So respectively, iodine is much larger than fluorine, correct? Right? Much, much larger. And that makes sense because iodine has a total of how many electrons? 53, right? That's a lot. That makes iodine huge, huge, right? Whereas chlorine only has like 17 total electrons. Not valence electrons, but total electrons, right? And so as we're going down the periodic table, right? As we're going down the periodic table, there's this thing that we use called the principal quantum number, okay? The principal quantum number. And it's very simple. The principal quantum number at the very top row is 1. At the second row is 2, 3, 4, and so on. So as the principal quantum number gets larger, yes, as the principal quantum number gets larger, so does the element. Does that make sense? Right? So does the element. Because the principal quantum number tells you how far the outer shell of an electron shell of the outer shell is of the atom is from the nucleus, right? So obviously down here, iodine is going to have a larger principal quantum number than what? Fluorine or chlorine, right? And then the other thing about it too is that as you go down the periodic table, your principal quantum number increases, right? And when the principal quantum number increases, what also happens? The attractive forces between the molecules, right? So at a principal quantum number of 3 here with chlorine, right? I think it's 3. With chlorine, right? the quantum at that point the attractive force isn't as strong. We'll talk about why later, right? But they're not as strong, and that's why chlorine is a gas. Okay, you go one down, its principal quantum number is one higher than chlorine, right? Which means it's got more electrons. The shells are spread, are the shells one shell wide, one more shell than chlorine, right? Bigger than chlorine, and now the intermolecular forces between the molecules are a little bit more attractive, and that's why they're liquids, right? And then when you get down to iodine at room temperature, it's got the highest principal quantum number of all these halogens. And what do you have? You have a solid, because that's where the intermolecular forces are the strongest, right? And the strongest are the most um, to hold them together as a solid. Does that make sense? And we'll talk about why in just a second. So keep that in mind about the principal quantum number. Pin that. So check this out, right? Here are some, properties of the different states of matter. Gases, right? Well, they assume both the volume and the shape of their container, which makes sense because if you have like a flask with chlorine gas in it, does all that chlorine gas stay at the bottom? No, it kind of just fills the entire flask, right? That's why you saw it in the picture of before as a green gas that was kind of just throughout the whole thing, right? They expand to fill their container. The thing about that too is that gases, they are definitely compressible, right? There's so much space between each of these gas molecules that you can actually push down and make the volume of the container smaller, and you can compress the gas, right? You can compress the gas. So um, that's why you guys ever use the canned air, right? Or even whipped cream or anything like that has, or even hairspray. When you start running out of, they actually compress all those gases, the hairspray molecules, or the I don't know what gases they use in the canned air. I have no idea what gas they use, but you turn it upside down and it freezes things, right? And so what happens is that they compress it all the way down, but then you start losing when you start spraying it, you start losing the gas molecules, and so the pressure isn't as high anymore. So as you keep on using it, you actually feel it get weaker and weaker as it comes out of the nozzle, right? So gases are compressible. They flow readily, of course, right? And diffusion within a gas occurs rapidly. Liquids, on the other hand, they actually assume the shape of a portion of the container it occupies, right? Because it kind of sits at the bottom like this. But the thing is, though, they're virtually incompressible. And the reason why is because these molecules right here are already too close to each other. Okay? They're already too close to each other. So you can't really compress them. They flow, and then diffusion with the liquid within the liquid occurs slowly, right? That's why when you're cooking and stuff, you got to mix things. It just doesn't mix together, okay? And then the last but not least, certainly, are the solids. They retain their own shape and their own volume, of course, like the table here, right? They do not expand to fit their containers. We'd have a problem if they did. Virtually incompressible. You could try to, right? It doesn't flow, and diffusion within a solid occurs extremely slowly, which makes sense, right? Makes sense, right? We've got a couple of different solids here. We have a crystalline solid, which is very ordered, and then we have an amorphous solid that's not as ordered as far as the atoms or the atoms go. So your very first question is this. Go ahead and scan it with your phones. Oh, I let my girlfriend borrow my laser, so I don't have that even with me either. Oh, yeah, I need to sign in to see how you guys answered here. Huh? That's fine. Just make sure you're on the Wesleyan Wi-Fi and it shouldn't ask you again after the first time. Hopefully. That's what we all hope. What happened? Really? You literally have to log in every single time? What's going on here? It wasn't like that before, was it? And does it send you that stupid code every time too? Yeah. Holy cannoli. Holy cannoli, yes. What? Huh. Yeah, that's what I'm saying. Me to sign in every time, gives me a code every single time. No matter how much I say, do not me to sign in again. The code just keeps doing it. Even if you're on the Wi-Fi? Yeah. The Texas Western Secure Wi-Fi? That's so weird. It doesn't do it to me. No, I guess it doesn't like this. So we should stop it. No. The best part is having you answer these questions, and then when you answer differently, you have to talk about it. So that's the best part of this thing. Okay, let's see how everybody answered. That is so weird though that some people don't have to, but some people have to sign in every time. Like this computer, for example, I sign in this computer at least twice a week, and for some reason, I have to freaking use my code every single time. Why can't it just stay signed in for me? Oh my god, sign in the code. Oh my god, what is happening here? Okay, finally, I'm into freaking this thing. And this question. It is. It is. No, I'm not saying that anything's wrong with it. I'm just saying that that's really weird because usually if you're on the Wi-Fi, it shouldn't ask you whether or not you're, every single time do a freaking, what is it called? Two-factor authentication. All right, so that was an easy question, right? Someone still got it wrong, but it was an easy question. The only thing that is compressible is a gas. Okay, the only thing that is compressible is a gas. So I guess I don't have to make you discuss that. Oh, you did not have to reveal that. That is. All right. So, all right. Where's my laser? I lost my laser. Here we go. Okay. So these are the three of the types of forces that we're going to be talking about today between the molecules. So just so you know that when I say intermolecular, right, the prefix inter means between. So intermolecular means between molecules. It's Greek for between. You'll also hear me say intramolecular, right? So that's INTRA, right? That's inside. So intra means inside, right? But inter means between. So right now we're talking about the molecular forces between the molecules, right? And three of them that we're talking about just right now are called the dispersion forces, also known as the London dispersion forces or the induced dipole interactions. Also, we're going to talk about the dipole forces and then hydrogen bonding, right? There are more than this, but we'll talk about these three first. But the thing I do want you to know, right, is that this right here, van der Waals forces right here, right, are these two right here are both known as van der Waals forces. Okay? So when I say that, that means I might ask you a question that says, which of the followings are considered van der Waals forces, right? So make sure you know that the van der Waals forces, oops, flashlight, sorry about that. The van der Waals forces are the dispersion forces and the dipole forces, okay? So let's first talk about talk about the dispersion forces, right? Usually this happens between nonpolar particles, right? That can be temporarily polarized to create a dispersion force. So here we have helium atoms, okay? Here we have helium atoms, right? And so the tendency of the electron cloud to distort is called polarizability, right? So check this out over here. We have an atom of helium right here. We know it's helium. Why? Not just because I said helium up here below, but if I didn't say that, how would you know that this is helium? Only has two electrons. Exactly. Right? Only has two electrons. And so right now, helium is just, they're by themselves, okay? They're not really doing anything with each other right now, okay? But in the next one, right, they're starting to come together. And this is that van der Waals graph I showed you before. Um, this thing right here. We talked about this last week, where we had the, oh, I better make sure I'm writing. Remember the van der Waals graph? This guy right here? And then it went down like this, and then went up like this, right? And this was the distance of the two atoms here, and this is the energy, right? You remember that graph? That's called a van der Waals graph, right? And as the molecules get closer and closer to each other, going in that direction, right? As they get closer and closer to each other, going in that direction, you can see what's happening here is that some of the electrons in helium B, right? Atom B or helium B right here, are making it the repel. So what did I tell you are the things that can repel? There's the nuclear forces repel, right? Nucleus can repel, right? And the electrons can repel each other, right? Those are both repulsion forces in molecules, right? And so here, helium B or atom B here, right? The electrons are starting to come together, and when they come together, they push or repel the electrons from atom A, right, further apart to the other side. Okay? And when then that happens, right, now the two electrons that were over here on atom B are attracted to what? The nucleus, because the nucleus is positive, right? And then on the other side of atom A, you have the other electrons that were pushed away by the electrons from atom B. So that's basically what's happening here, right? We have the electrons up here, or it's not the electrons, but the atoms up here, and they're getting closer and closer and closer together, right? And during this part right here is when the electrons from one atom are pushing or repelling the other electrons out of the way, right here, right? So what is this part right here when we're at the lowest energy? This part right here when we're at the lowest energy is when the electrons are now doing what? They're being attracted to the nucleus because the nucleus is positive. So that's called an electrostatic attraction right there, okay? And the reason why we call this, excuse me, polarizability is because when you look at the atom down here, we see that there's a partial positive charge of the atom B on the right side and a partial negative charge of atom B on the left side. And then the same thing is true of atom A. And when that happens, what do you get? You get negative and positive attracting to each other, right? Because opposites attract. This is a dipole because one side is positive and the other side is negative. Does that make sense? Right? So, I already talked to you a second ago about the principal quantum number, right? So here's the statement that you need to remember right here. As the principal quantum number of valence electron shell increases, what that means is as we go down the periodic table, right? Because the number is increasing, okay? The polarizability increases, okay? The polarizability increases. Why do you think that is? Why do you think it is that when you get bigger and bigger and bigger, as far as an atom goes, that, and it means the same thing as the principal quantum number getting larger as well, right? Why do you think that increases polarizability? Exactly right. There are more electrons, right? And when there's more electrons on one side, right, there's more of an empty gap on the other side. What do you have? A huge polarizability, right? One side's super negative and the other side's super positive. Does that make sense? Right? So that is a trend that you must know. Because I will ask you questions about that trend. I won't ask you questions about this actual definition, right? But I will ask you questions about that trend. Okay, so let's talk about some more factors that affect the dispersion force of a molecule, right? Again, we just, Stephanie just said this, the number of electrons in an atom, right, affect it. So the more the electrons, the more the what? The more the the more the dispersion force, there's the word, right? As the size of the atom or molecule increases in weight, there's more dispersion force. Because the only way that an atom can increase in weight right, is if it gets bigger, and it means it has more electrons, right? Does that make sense? Okay. And then the shape of the molecule with similar masses can also impact it, right? And so when you have molecules that are the same, similar shape and similar masses, they'll contact with each other, and then you'll get less of a dispersion force, right? So these two up here make you have, if you get bigger of each, right, they make you have more dispersion force. And then down here, this one here makes you less dispersion force. So this graph here shows you a demonstration, right, of the dispersion force, okay? Here's pentane, right? And pentane is the molecule C5H12 right here. And as we go up, here's hexane, C6H14, and then we have heptane, C716. These molecules get bigger and bigger and bigger, right? And as they get bigger and bigger and bigger, what happens there? The molar mass gets bigger, right? What else gets bigger? The boiling point, right? So the more electrons there are, the more dispersion forces there is, right? The higher the what? The boiling point, because you have to have more energy to do what? To disrupt those dispersion forces, right? Because when you're trying to boil something, what are you trying to do? You're trying to evaporate it. You're trying to turn it from a liquid to a gas, correct? Right? And when you're trying to make it a liquid from a gas, you're literally disrupting the dispersion forces that are between two molecules so that they break apart and become a vapor, right? Become a gas. So here you can see as you get more and more carbons, and more hydrogens, you get more and more electrons. There's more of a dispersion force, right? And you get a higher boiling point. Okay, you get a higher boiling point. You get a higher boiling point. So interestingly enough, that's what we see here with the linear molecules, right? But then if you have a spherical molecule like this guy right here, this is neopentane, right? Neopentane is a molecule that's the same thing as pentane, except that it's arranged so that it's kind of like a shape of a ball, right? Since they're in the shape of a ball, there's less dispersion force with those. So that's why we're talking about the shape, right? With similar masses and more compact will give you less dispersion force. Because it makes sense that two balls being packed together is smaller, right? Than two long pieces of carbons packed together. Does that make sense? It's more compressed, right? It's like the difference between having a piece of paper that's all flat and then crumbling it into a ball. Does that make sense? Because the ball has less surface area, right, than the thing that's stretched out does, just like a piece of paper. Okay? So, again, polarizability has an effect on boiling point right here, right? Remember, this means less intermolecular force, smaller molecule, atom, lower molecular weight means fewer electrons, right? So notice that neon here and fluorine, right, their boiling points are pretty low, right? Because they're pretty small, right? They're pretty small. As you get bigger and go down the periodic table to chlorine and bromine, argon and krypton, xenon, and you start getting a boiling point that's super high because the bigger the molecule, right? The bigger the molecule or the bigger the atom, the more dispersion force there is because there's more electrons to be attracted to the nucleus, right? I've harped this now on this now for 3 slides, right? So do not forget this, okay? Here's your next question. Don't forget to scan. I'm sorry if you have to log in every time. That's how we do our attendance. They're really harping attendance this semester for some reason. I've gotten like 8 emails in the last like 2 hours. Do your attendance, do your attendance. So I'm glad everybody's here because I can just say everybody's here. Daniel, have you scanned? All right, let's see where we're at. I've got 5 responses so far, 7 so far. Still waiting on 4 more. Two more. One more. Take your time. We're going to be talking about this for the next couple of days, so no rush. I'm glad you guys got the notes though, because I posted them like at midnight last night. Maybe it was 3 in the morning. I don't know. It was either 3 in the morning or at midnight. So it's hard for me to tell these days what time it is. Okay, everybody's logged in. I mean, sorry, not logged in, but answered. Let's see what everybody says. So the vast majority of people said the butterfly. The vast majority of people said A, which is the principal quantum number. But then we had 3 people that said D, all of the above, right? So I just want to say that in the previous slides, I never once mentioned anything about the first ionization energy. I never mentioned anything about uh, what was that other one? Effective nuclear charge, right? So the answer here, right, is A, because as you get down the periodic table, as you go down the periodic table, the principal quantum number increases, which means that the number of electrons increases, the size of the atom increases, right? And that gives you more dispersion force, right? That gives you a stronger dispersion force. Okay? All right. So now that we've flogged that dead horse, known as dispersion forces, let's flog another dead horse. It's going to be the dipole-dipole interactions now, right? I know that as you go through these, they're going to look very similar to each other. Okay, they're going to look very similar because in the end, they're all some kind of attraction, right? Through opposites attract, but there's very subtle differences, and you'll see what they are. You know, when we get a big chart, what I like to call the "you're welcome" chart, right? At the end of all this, okay? So dipole-dipole interactions usually only occur with polar molecules, right? So remember that in the dispersion forces, we had nonpolar molecules, correct? Right? We had things like bromine, 2 bromines together, right? Br2 or Cl2. They're the same thing on both sides, so they're nonpolar, okay? But here we have this right here, right? Which I think is this formaldehyde? No, it's not formaldehyde. Acetate, maybe? Yeah, maybe. Um, I lost my train of thought. Anyway, the point is, this molecule here is definitely not nonpolar, okay? It's definitely not nonpolar. It's polar. Why is it polar? Exactly. We have an oxygen at the top, right? The oxygen is electronegative. The rest of this part here, the methyl groups, right, are not electronegative, are they? They're actually very positive, partially positive, right? In fact, you'll learn in organic chemistry that the oxygen up here will draw electron density away from this carbon, make it even more partial positive. Okay? So this molecule is definitely not nonpolar. It is definitely polar. Positive on this side, negative on this side. And so you can see here that's borne out in this electrostatic potential map, right? Very red up here, red it's always negative, and then down here it's very blue because it's very positive. Does that make sense? So what can happen then is if you have 2 of these together, right? You have 2 of these together, the negatively charged or the partially negative oxygen will attract itself to what? The partially positive carbon, right? The partially positive carbon. You can see here in this electrostatic potential map here, right? Where the negative, right? I mean, see it here in the signs, of course, but you can also see what it looks like as far as the charge distribution goes. The red part is really attracted to the blue part, right? And that is called the dipole-dipole interaction, right? Opposite charges, oppositely charged ends attract each other. Okay, that's a dipole-dipole interaction. Whew, good stuff. So we can look at these molecules here. Remember propane? Remember propane, right? Here's propane, and we saw propane in the 2 slides ago, right? 2 slides ago, and it had a boiling point of 231 Kelvin. Okay, that's propane right there. And propane exhibited what kind of interaction? Not this one. What did propane exhibit? It was the first interaction we talked about. Dispersions, right? Dispersion forces. So propane experiencing dispersion forces, right, has a boiling point of 231 K. Okay. But then we get here to dimethyl ether. Oh, that's what that was. That was dimethyl ether. Was that dimethyl ether? No, that wasn't dimethyl ether. What I had over before is not even on here. Oh, we have dimethyl ether now, which is definitely a polar molecule because it has an oxygen right there, right? Look at this boiling point. It's higher, right? We get even more polarity as we go and get to acetaldehyde, and we get to acetaldehyde with even more polarity because of the oxygen up here being really negative, partially negative, and the carbon over here being partially positive, but even more extreme in those cases. And its boiling point is 294. And then we get over here acetonitrile, right? And we have nitrogen now here on this side, and we have carbons on that side, even more polarity, and we get a boiling point of 335 Kelvin, right? So another trend, as increasing polarity happens, right? Increasing dipole interactions occur, which do what? Cause a higher boiling point, because you need more energy to break those to break those interactions to evaporate it, right? So again, though, for molecules of approximately equal mass and size, the more polar the molecule, the higher the boiling point. See? So I always have these little last statements here that will be like, an exclamation mark on what I just said out loud. Everybody understand? It's pretty simple so far, right? Pretty simple. Really, right now, all you have to do is memorize these definitions. Okay? All right, here's your next question. Excuse me. Let's see. Where are we at now? Polarization. I already did that one. There we go. Okay, 4 people have responded. Has everybody scanned it? All right, so far 8, 9 people, 10 people have responded. 12, 11 people, one more person. Awesome. Say again? Oh, I forgot. I keep forgetting to do that. I mean, they're going to be in the video, so they'll be in the video. But it's hard for me to go back and put it into the notes that are already posted on Blackboard. Does that make sense? All the questions? Hmm. I'll try. We'll see how that goes. But again, it's going to be in the video, right? So it'll be in the video, and then you're going to hear me talking about it in the video. All right. This is the perfect one to get you guys to discuss because it's half and half. Look at that. So get together with the groups and talk about it. Your houses. Why do one of you think it's one thing or the other? Right? Huh? Oh yeah. Here's the question. Talk about it. Because half of you think it's one thing and half of you think it's another thing. Why? Have you guys talked about it? Oh, you all have the same answer? Oh, don't say anything yet. We'll see if we'll see. Log in again. Well, don't scan it yet. I haven't put up the new I haven't put the new one up yet. Okay, how has everybody come to a consensus? Not yet. Let's talk about it. Oh, look at you handwriting notes. Tired, but it's Monday. I know, and I'm like, am I not like entertaining enough today? I know this stuff is so boring.
It's funny because in my sociology class, like, I was like, okay, I'm ready for the day. And then whenever I walked over here, I was like, I'm really tired.
Well, it is kind of a dark day outside too.
It's kind of cloudy.
It's a little cloudy.
I hope it rains. I love when it rains.
Me too.
When it rains, I want to.
I need my grass watered in my front yard. All right, everybody got it? Okay, scan it again right now. I put up the new one already. Scan it again. Let's see if we all get the same answer this time. I'm really sorry about that. I have no idea what's going on with that.
I just decided to make it super complicated because I don't know what you're talking about. No, it is so complicated too. There are so many things involved in that. Both of y'all? Both of y'all?
One more person. I am so proud. Because you all, well, most of you answered correctly. Good job. The answer is B. The reason why the answer is B, oh shit, excuse me. There's still one more person. Whoever that is, put in your answer. Was it you two? Did you put in your answer? I need you to get your answer in there so that it says, there we go. Good. Okay. Good. Okay. I think two cheated a little there, but that's okay. I'm totally kidding. No, so literally, the thing that gives you the clue here is that the two things are comparable in size and shape, right? So, for example, um, uh, uh, um, I forgot what I was going to say. But anyway, they're comparable in size and shape. And there's a slide that I wrote in there, right, previously, that literally says that when they're comparable in size and shape, dipole-dipole interactions are going to be more prevalent, right? They're going to be the dominating force, right? Yeah. So the reason why, so if this had actually said they were different size and shape, right, then it would be the dispersion force, which is A, right? Then it would be dispersion force if they were different size and shape. Okay, so that's the thing you need to remember. If you can't find it in my notes right now, write it down right now. Okay, if two molecules are comparable size and shape, dipole-dipole interactions will likely be the dominating force. Okay. If two molecules are comparable size and shape, dipole-dipole interactions will be the dominating force. Okay? It's already in your notes somewhere, but you can write it down again. But if one molecule is much larger than the other molecule, then dispersion, I keep on saying dispersion forces will likely be the dominating force. Everybody get that? So comparable size, dipole-dipole, right? Two different sizes, dispersion force. Okay? All righty. Okay, so let's go ahead and talk about my favorite type of intermolecular. Sorry, I think I just shot the laser at someone's eye. My favorite type of intermolecular forces, and that is the hydrogen bond, right? So hydrogen bonding is actually a type of dipole-dipole interaction, right? Because you have things that are positive on one side, negative on the other side, attracting to each other. But the interesting thing about it is that usually in a hydrogen bond, there are, what happened?
I'm sorry.
That's going to be on the video. So, so anyway, so dipole-dipole interactions are very similar. Sorry, let me say that again. See, you've messed up my flow. Hydrogen bonding interactions are actually very similar to dipole-dipole interactions because you have something that's super positive on one side and negative on the other side, and they're attracting each other oppositely. What difference is, though, that hydrogen bonding usually occurs with hydrogens, right? And they're bonded to electronegative atoms like nitrogen, oxygen, or fluorine, and they're super strong, okay? They're super strong. So literally things like water are held together with hydrogen bonding, right? Your DNA is held together with hydrogen bonding, right? If you think about the A's and the T's, right? What does A and T stand for in DNA? Adenine, right? And T in thymine. So adenine and thymine are held together in your DNA with two hydrogen bonds, right? And then there's also G and C. What does G and C stand for? Guanine and cytosine, right? They're held together with They're held together with three hydrogen bonds in your DNA, right? So what do you think is stronger? The hydrogen bonding between adenine and thymine, or guanine and cytosine? Guanine and cytosine, because there's three hydrogen bonds to deal with, right? So I don't know how many of you want to go be scientists later on in life, right? But when you're doing something called PCR, the polymerase chain reaction, the most widely used technique in all of science to amplify DNA, right? You have to make sure that the sequence that you're trying to amplify doesn't have too many G's and C's. Because if there's too many G's and C's, right, it won't unzip correctly so that you can actually make a good product from that reaction. And you'll learn more about PCR when you get to like biochem, right? But one of the things that you have to worry about is the GC content, right? And if the GC content is too high, you're not going to have a successful reaction. And the reason why is because hydrogen bonding is unusually strong, right? And the more hydrogen bonds you have, the stronger it is, right? So you don't even know how many. I must have run at least 10,000 PCRs in my career, okay? Because PCR is such a huge, huge thing that's done in biomedical research, okay? Hydrogen bonding is an attraction between a hydrogen atom attached to a highly electronegative atom and nearby small electronegative atoms of a smaller chemical group, right? Oh, I keep on getting the butterfly.
I saw this really pretty yellow and black butterfly today. I took a video of it.
Really? That's cool. So if you take a look at water here, right? You have water with its, remember I said intramolecular? So intra means inside the molecule, right? That's the covalent bond. So don't be surprised if I ask you a question, right? Which is an intramolecular force? And it lists out covalent bond, ionic bond, and van der Waals interaction, right? So the two that are actually intramolecular are what? Covalent and ionic bonds. So here we have water, which is it has an intermolecular bond between covalent bond between the hydrogen and the oxygen, right? But then the water molecule is attracted to another water molecule using hydrogen bonding, which is the intermolecular force. Okay? And so here we have a positively charged hydrogen, right? And it's attracted to the negatively, partially negative oxygen because of the electron lone pairs right there, right? So the important thing to know here is that for hydrogen bonding to occur, right, there has to be lone pairs available, right? And then on the other molecule, the hydrogen also has to be attached to another electronegative atom that has lone pairs. Why is that? It's because remember what I said before. I talked about it with the oxygen and the carbon, but the same thing happens here with the water. The lone pairs of the oxygen, right, and this oxygen itself, since it's so electronegative, will draw electron density away from the hydrogen right there, making the hydrogen more positive, right, and then making the nitrogen more negative. Sorry, the oxygen more negative. Same thing happens on this one, right? The oxygen is more negative here because it's drawing electron density away from the hydrogen, right? And so now these hydrogens are super partially positive, these oxygens are super partially negative, right? And they're attracting each other really strong with a hydrogen bond, right? So remember, not only does it have to be a nitrogen, oxygen, or fluorine, there has to be electron pairs, lone pairs available too. A hydrogen bond can't happen unless there's a lone pair there, okay? So here we have hydrogen fluoride, right? Hydrogen fluoride. The oxygen up here is just like the fluorine down here, drawing electron density away. So the fluorine is super partially negative. Hydrogen here is super partially positive, and so they make a hydrogen bond. Here's another very common hydrogen bond. You'll see this all over biochemistry, all over your DNA, right? Nitrogen, electronegative, drawing electron density away from itself, and then the hydrogen partially positive on the next ammonia right here, and then you have a hydrogen bond in between. See, you see how you notice how this hydrogen right here is literally hydrogen bonding. It looks like it's hydrogen bonding to the lone pair, right? Lone pair again, lone pair again. It can even happen between a nitrogen of ammonia and the hydrogen from a water, right? As long as there's a central atom here with a lone pair and it's an electronegative atom, right? And the hydrogen here is also attached to another atom that has lone pairs. Same thing can happen on the other side too, right? One of the hydrogens from the nitrogen is now hydrogen bonding to the lone pair of the oxygen. Okay? So lone pairs are super important in this case. Super important. Make sense? Okay? Makes sense. Good, good. Okay. So this is just an interesting graph that I wanted to show you because if you look at hydrogen bonding with water right here, right, it's got a boiling point all the way up here at 100 degrees Celsius. But then there's hydrogen bonding with hydrogen fluoride, right? And then ammonia and methane. That methane actually doesn't have any hydrogen bonding at all, right? Because is there any lone pairs in that carbon? No. So there can't be any hydrogen bonding with methane, right? But the interesting thing to notice here is that the hydrogen bonding between water, right, molecules is so strong that you need 100 degrees Celsius to boil the water to break those hydrogen bonds, right? But then you compare it to all the other ones, much weaker, right? This boiling point is like hydrogen fluoride. Holy, I mean, that's what is that, 30 or 20 degrees? Ammonia's is like less than freezing point, right? And it gets even worse when you come out here when you get the hydrogen. So here's water right here, right? H2O. But then here is H2S, which is literally the same thing because sulfur is just below oxygen in the same group, right? But so you would think it would act the same, pretty much. But for water and then hydrogen sulfide right here, right? Like there's a huge disparity in the boiling points. And hydrogen sulfide gas, which is actually what makes your fart smell and what you smell when you have a gas leak in your house, right? Hydrogen sulfide, right? Its boiling point is less than freezing point, but water is up here. So there's something very special about the hydrogen bonding with water. Does that make sense? Water is special. All right, next question. I know somehow I knew that there would be it'd be low energy today in here. So there's like a question after every every slide. I understand though. I'm a little low energy myself. I didn't go to bed till like 3 o'clock last night. because I was making your notes.
Oh, so it's our fault.
Yeah, it is. I mean, I could not provide you notes at all. So, I mean, do your other professors give you notes to write on? So, and a video?
Yeah, you're just the best ever.
Thanks, I appreciate that.
I really think that's what they do.
Yes, I just need my horn tooted a little more. I am dedicated to you guys. What's wrong? I said I'm very dedicated to you guys. So, as tired as I am, I'm very dedicated to you. Because I want you to learn chemistry. Chemistry is so much fun. Man, I was in my non-majors class on Saturday, and we were talking about ionic bonds, and somehow it devolved into talking about like swinger parties. Yeah. Yeah. Because think about it, right? Ionic bonds and covalent bonds, right? Like covalent bonds are like when you have like a chlorine and a chlorine together, an oxygen together, right? And so they like to be with themselves. It's almost incestuous, right? It's like, a brother and a brother being together, right? Whereas if you have something that's ionic, right? Almost always an ionic is always going to be something two completely different things, right? And then there's some ionic compounds, for example, magnesium, right, that needs more than one chlorine. It needs two chlorines to be happy. So he's swinging, right? They're in a polyamorous relationship. So quite literally, every single element on the periodic table acts like a person, right? And they have their preferences, right? Their goal is to get octet of 8, right? But the way of getting it is different for every atom, right? So it just depends. It's crazy stuff right there. So I wouldn't say it devolved. It actually evolved into a conversation about that stuff, and it actually helped my students understand it very well. So let's see what the responses are. This is one of those questions I literally just spoke about. So let's make sure we got this. Don't worry, I'll clip that part out. So okay, we have 11 responses. 2, is that you again? That's missing up there? Okay, we still need one more response. Who's not done it yet? Who's not done it yet? Still waiting for the last person. Who's the last person? Huh? Has everybody done it already?
Oh, I didn't split it.
There we go. Okay. I was like, who the heck? All right. So this is one of the questions. This question literally is a question of the last slide I just talked about, right? To form a hydrogen bond, what must the non-hydrogen atom involved in have in the bond process, right? So the answers were, let me switch over. There we go. The answers were the non-hydrogen atom must have an electron pair, non-bonding electron pair. Hydrogen atom must have low electronegativity. Atomic number, size, blah, blah, all that stuff is wrong. The first one is correct, right? Because I literally, in the very previous slide, I literally said that the non-hydrogen atom had to have a lone pair, right? So I'm glad you got that right. Most of you, anyway. Okay? The 2 who didn't get it right, something to memorize. Okay? Okay. Let's keep on trucking here. Let's talk about some water here, right? So we've talked about this a little bit before already in one of our previous lectures, but hydrogen bonding, right, is very special in water, right? And there we go. It's hydrogen bonding that actually makes ice less dense than water, right? Than liquid water, right? Because when the hydrogen bonding in water gets frozen, it actually makes the molecules of water further apart, right? Further apart. and it forms into the very linear, special way, right? Uh, very organized way. Okay. If this were water in liquid form over here, okay, in liquid form, these would all be all over the place, right? It'd be very random. But since there's hydrogen bonding occurring right here and it's freezing, these hydrogen bonds freeze in a very organized way, making these ice crystals, like in the snowflake right here, which that is some very clear water. I made that. Anyway, right? And that's why water is actually more dense than ice, and that's why ice floats in your water, okay? Excuse me. And then I guess the other thing I want you to notice too is the distance here, right? The one of the things that actually denotes whether or not something is a chemical bond or if it's an intermolecular interaction is the distance from one atom to the next. Notice here in this covalent bond here, right, we have 1 angstrom, right, is the distance. But then in hydrogen bonding, the distance is like 1.8 angstroms. You notice that the distance is much further apart, right? So that's another thing that you need to take note of. And then, as always, since we did VSEPR recently, what is the bond angle of water? Anybody remember what the bond angle of water is? Yes, 109, 109 degrees, okay? Because water is what? A tetrahedral. And tetrahedrals have what? 109-degree bond angles, right? Yes, write that down. All right. So now we're going to move into the other intermolecular interactions, right, that are not hydrogen bonding, dipole-dipole, or dispersion. This is called the ion-dipole interaction, okay? And in an ion-dipole interaction, what literally is happening here is we're dissolving salt into water, right? And we already know that salt is made of sodium chloride, right? And sodium is over here on the periodic table on the alkali metals. It's got a positive charge, right? Because it lost an electron, so we had a full outer shell. Remember that? And then chlorine here, right? It's pushy, right? It's one of those elements that gives and that takes, right? Uh, literally, in the relationship of sodium and chloride, if they were in a relationship, it's clearly a give-take relationship. It's definitely not a give-give, right? It's a give-take because sodium is giving chlorine an electron, and literally chlorine is just taking it, right? And so when that happens, chlorine has an extra electron and it's negative. And then sodium has one less electron and it's positive. Well, that's great. Why is that great? Because when you put it in the water, water molecules can surround them, right? The partially negative oxygens on the water molecule will be attracted to what? The positive sodium ions, right? And it will literally surround the sodium ions, okay? And then for chlorine or the chloride ion, right, it's negative. So the partially positive hydrogen sides of the water molecules, right, will surround the chlorine molecule. And this quite literally is how you dissolve things, okay? Water, right, will go in and surround an ion, right, with one side positive, the hydrogen side being surrounding the negative ion, right, or the anion, and then the other side of water, being the negative side, will surround the positive ion. And it happens with every single ion we do, right? If this were magnesium chloride, it would do the same thing. If it was magnesium fluoride, it would do the same thing. And that's the reason why water is such a great solvent. Use water for all kinds of stuff because it can do this kind of thing so efficiently that it can dissolve almost anything, right? It can dissolve almost anything. So here, right, here in ion dipole interactions, the thing you need to remember, right, is that water's partial negative side, right, will surround a positive ion, right, and then water's partial positive side will surround a negative ion, and that's how you dissolve things. That's how salt gets dissolved in water, right? Oops, I'm glad nobody was there, right? Next question. I'm telling you, I put a question after every single one because I knew that today would be a low energy day because I'm low energy today. And it's making me more excited when you answer these questions correctly. I'm so sorry, Vanessa. I almost hit you with this meter stick.
No.
All right, this one is called so far only 3 people have responded. Eight responses so far, and so far so good. It means you're actually paying attention to me, which makes me feel good about myself, as if I need to feel any more good about myself. 10 responses so far. Twelve responses. Let's see what everybody said. Overwhelmingly, the answer is D, because everybody got it right. The reason why is because the negatively charged oxygen, right, is attracted to the positively charged sodium. Good job. High five. What the heck? Only the Slytherins freaking high fived me. What's wrong with you people? 1 point for Slytherin. Jesus. I did. Sorry about that. All right. We're almost done with today's lecture. Okay, we're almost done. Only 5 more minutes left. And then you need to get ready for your quiz when Ms. Dickens gets in here, right? All right. Huh? Mm-hmm. Huh? Oh crap, we are doing it there. You're right. Thank you for saying that because my boss is actually in here after us. So good thing you said that. The guy that was in here earlier with the all the organic molecules. Okay, so here is your welcome chart. For now on, when I give you a chart that summarizes everything, right, where you can just memorize that chart, you'll get 90% of the questions right. Right. I'm gonna call it the you welcome chart, and then one day I'll actually play the song for you. Okay, from Moana. This is the you welcome chart. You don't have to take a picture. It's on Facebook. Blackboard. It's on. I can post it on my Facebook. It's on Blackboard. All right. So notice, right? We have. Flashlight. There we go. Notice we have all the 4 types of bond intermolecular forces I was talking about: dispersion, dipole, hydrogen bonding, and ion. Right. And notice how the strength gets larger, right? As you go from dispersion dipole to hydrogen to dipole to ion dipole, right? You can even see here, right, what they look like. Here's your dispersion forces right here, right? The electrons are pushed to one side, right? Here we have dipole-dipole, where it's not the same atoms. It's always molecules that are polar, right? See, all molecules and atoms. Then polar molecules, right? Then we have hydrogen bonding, right? Here's your water molecules, hydrogen bonding to each other. Usually bonded, an H bonded to a fluorine, oxygen, or nitrogen. And then we have ion dipole here, where we have waters here solvating, dissolving. What is that in the middle there? What is that in the middle? Well, on the previous slide, it was a sodium, right? But really, it could be any of the alkali earths, right? Or the alkali metals, okay? So that's your welcome chart right there. But I'm so generous today. I'm so generous that I gave you a second your welcome chart. I'm so generous, okay? Because here, it actually tells you so in the previous slide, right? In the previous slide, all I really gave you is the kilojoules required, right, to break these bonds. But is that really like something that's like changeable? Because you don't really know what a kilojoule is, except for that, 1 joule is 1,000 calories or something like that, right? No, wait, 1 joule equals. Oh, wait, I'm sorry, I said that wrong. 1,000. That's 4.184 is what it is, not 1,000. I just rattling numbers off my head. But see, that's the thing. The number of joules isn't something that's tangible or easily remembered, right? But in this you welcome chart, look at this. In this you welcome chart right here, okay? Not only did I give you the strengths and examples of the intermolecular forces right here, right? I gave you their melting points, and I gave you their boiling points, and I compared them to what? Ionic bonds, metallic bonds, and covalent bonds, the stuff we talked about last week, right? Because guaranteed, I will ask you a question about what is stronger or what's going to break what, and blah, 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 blah. How much energy for this, how much thing for that. And notice, down here, when we have dispersion forces, right, the boiling point is 77K, which is like really low, by the way, right? Dipole-dipole interaction, boiling point is what? 188K, really low. Hydrogen bonding, 193K, about 100 degrees Celsius. So it's stronger, right? Because that's what DNA is. That's what water is. That's why you got to go to 100 degrees to boil water, right? That's why when you're doing PCR reactions, you're trying to break apart the DNA molecule, unzip it. You have to use 95 degrees because you need to break apart those hydrogen bonds. But then we go up to the chemical bonds. Look how strong these things are. Covalent bonds, right? Boiling point 4,300K, right? Metallic bonds 3,742K, right? Almost 2,000K for ionic bonds. Remember how much energy it takes to melt and evaporate a piece of salt? It's crazy, right? So this chart here, this You Welcome chart here, gives you the strengths and its relationship and how it affects its boiling point and its melting point. Make sure you don't have to memorize the exact numbers, but at least memorize the order, right? The order of the strength, okay? And whatever the heck I wrote down there. What did I write down there? Um, I'm talking so fast, so loud, I don't even know what I wrote on the slide. Intermolecular attractions are weaker than bonds, and then hydrogen bonds are not chemical bonds. And remember, they're not chemical bonds because that was based on the distance, right? The length of the bond. Remember that the covalent bond was like 1 angstrom between hydrogen and oxygen, but then the hydrogen bond between the hydrogen and the other oxygen was what? 1.8 angstroms, right? So the distance also tells you whether or not it's a bond, chemical bond. All right, this is the last thing we're doing for today, is this question. Whew. I am like, I'm literally out of breath. So I feel like I'm screaming this stuff at the top of my lungs. Am I doing that? Am I being really loud? I apologize. But I want the entire campus to hear me say this. All right. Let's see how everybody is doing. So far, only 2 people have responded. Let's not think about it too much, okay? I literally just gave you the You Welcome chart, okay? I literally just gave you the You Welcome chart. One thing I don't want you to think about too hard is what I've told you, okay? Just read what I wrote and what I said and just do it. Don't think about it too much.
Oh my god.
Because I'm not trying to trick you. I'm so sorry. Do you guys have to put in your codes? So it's just Hannah?
This school doesn't like me, I guess.
Really? I thought the school liked everybody. It says in our thing, we love everybody. Everybody come. Please give us your tuition money. So that's what I thought the school, I thought the school loved everybody. Okay. 8 people so far, 9 people, 10 people. Almost there. 2 more people. 2 more people. 2 more people. 11 people. 1 more person. There we go. Let's take a look at this and we can end the class. The vast majority of people said A, right? Which is correct because A is methanol, right? And if you write out A, you draw it out, methanol, and you draw it out, this is what it looks like. What thing? What happened? Yeah, it was at the chart. But that's okay though, because if you look at,
We're not saying that. We're saying like we're comparing what nitrogen is compared to all these other things. So that's right.
yes.
Because I got that wrong because I was looking at that stuff.
Okay, so the reason why it's answered this one, right? For one thing, you already know that carbon monoxide is a gas at room temperature. You already know that nitrogen is a gas at room temperature. So literally the highest boiling point is going to be the one that's not, the gas at room temperature, which is methanol, right? Because this is methanol. But the other thing to notice too is that methanol has an OH right here, right? And so when you draw out methanol, like this, you have an OH right there, right? What does that oxygen have on it, on the OH? It's got 2 lone pairs on it, right? And so those 2 lone pairs can do what? Hydrogen bonding. And hydrogen bonding has what? The highest boiling points. It's the strongest out of all the intermolecular interactions we talked about. And that ends lecture for today. Thank you very much for coming. Same time on Wednesday, please. Come again.